Well, this is it. We are finally at the point where we will have a functioning CPU. Last time, I went over the creation and testing of the final piece of the puzzle, the control block. And with that done, we can now finish the simple CPU. Albeit simple, with only 256 bytes of memory, it will be able to run instructions and manipulate data. So stick around as I put the finishing touches on the design, wire up some external RAM, and a way to program it, connect an output port, and write a simple assembly program to show it all working. Have you ever wondered how you can make your own CPU or microcontroller? Have you ever been curious about field programmable gate arrays, also known as FPGAs, but find them to be mysterious black boxes? Or wished you had a microcontroller-like device with a larger memory address or a wider data bus? Well, stay tuned as we delve into the world of FPGAs and create a CPU and eventual microcontroller from scratch. Hello and welcome to 100 Random Tasks. I'm your host, Philip Lett, and if you like what you see here, please give us a like and leave a comment. And subscribe if you want to be notified when more videos are uploaded, and it would really help the channel. With that, let's finish this simple CPU. Here's the CPU so far, and we can use the control block that we previously created in the last video directly, so I'll add a copy of it to the project. Let's have a look at it first. We don't need the clear output, but we still need it to exist, so we'll comment it out and add the clear internal wire. And don't forget to remove the comma after the CNT output, or you will get errors when checking the syntax. Next, we create the schematic block as before, and add it to the schematic. In order to keep things less cluttered, I'll only connect a few of the lines, and the others will be labeled. Like other schematic capture programs, labeling wires with the same name assumes that they are connected. So I'll go ahead and make the connections and label everything. With everything labeled, I'll add the output markers for the read, write, and count lines to make them external. With that, the control block is added, but there are still a couple of things to do before we can implement this design. First, if we look at the ALU block, the four operations originally were add, subtract, logical AND, and logical OR. But the control block has add, pass-through, logical AND, and complement. So we have to adjust the ALU to match. So I'll change case 1 to set internal to B. And set case 3 to complement A. And that takes care of the ALU. The last thing to take care of is the output enable for the I/O buffer and the address bus output buffer. If the CPU is the only device that can access memory, then it's simply a matter of tying the address bus enable low and connecting the output enable of the I/O buffer to the write line. Since if the CPU is writing to memory, it pulls the write line low, which then sends data out to the external data bus. When it's high, the data bus lines are inputs. But the test circuit that I will be creating will need to take control of the address and data buses to be able to program the RAM, so a way of disabling them is needed. For that, I'm going to add another input line called bus enable. When it's pulled low, it will disable both buses. The address bus buffer is active low. So if the bus enable line is low, we need the address buffer to be high. This is easily done with an inverter. The I/O buffer is a little more complicated since we have to consider the write line also. If the bus enable is high and the write is low, the I/O buffer enable should be low. In all other cases, the I/O buffer should be high. For that, a NAND gate with the write input inverted is what will be needed, so I'll add that now. And there's the finished simple CPU ready to go. Just a matter of implementing and generating the programming file. Now let's have a look at the test schematic. The RAM chip is on the right, and I happen to have a 6116 2K by 8 static RAM. The data bus is directly connected to the CPU, as well as A0 to A3 from the address bus. I only need the bottom 4 lines for the program I'm going to test. The other address lines on the RAM are tied low, except for A7. That's because I'm going to use it to decode an output port as well. So A7 will be connected to the chip select line of the RAM, meaning that the memory map is 00 to 7F for RAM, and the output port will be from 80 to FF. If you then tie the read line to the OE pin, and the write line to the WE pin, you would have the minimal connections needed to run the CPU. But we also need a way to program the RAM to give the CPU something to do. And that's what all this on the left is for. Basically, there are two 74-245 buffers that connect to the address and data buses, which are driven by dip switches, 4 for the address and 8 for the data. Their output is controlled by 2 push buttons, one for read and one for write. The bus enable line is created by ANDing the read and the write button states together. If either is pulled low, the bus enable line goes low, since if we press either, we want to use the dip switches to control the RAM and disable the CPU buses. So this line is connected to the bus enable line that was added to the CPU. There are also 2 other AND gates to control the OE and WE pins. If the read button is pressed, it forces the AND gate low, regardless of the state of the read line from the CPU. If the read button is high, then the state of the read line from the CPU is passed to the OE pin. The same thing happens with the write button, only controlling the WE pin. When we press the read or write button, we want to take control of the address bus. We can use the bus enable line to do that, since it goes low if either button is pressed. By connecting it to the output enable pin of the address dip switch buffer, it will output the address selected by the dip switches. The data bus, on the other hand, should only be driven if the write button is pressed. So the OE of the data dip switches is connected to the write button. If the read button is pressed, we want the data in RAM on the data bus, and the dip switch buffer disabled. Lastly, I've also added LEDs to all the lines to monitor their activity as the program runs. 8 for the data bus, 4 for the address bus, A0 to A3, plus A7, as well as 1 each for the read and write lines. With that explanation done, let's wire this up. We're almost ready to write the assembly program, but as I mentioned earlier, there will also be an output port. This is quite simple and uses a 74-574 latch. The OE pin is tied low, so the output is always on and displayed using 8 LEDs. The input is connected directly to the data bus, and we want the data to be saved when A7 is high, the right line is low, and the clock goes from low to high. To do this, a 3-input AND gate is needed, with the right line inverted as I've shown here. I don't have any 3-input AND gates, so I'll create the same thing using 2-input AND gates, which will give us the same result. Let's add this to the computer now. Okay, so everything's wired up, and here on the left we have our address lines, A0 through A3 plus A7. Next to that is our RAM chip, 2K by 8, followed by the 8 data bus LEDs, the 3 state count LEDs, and finally on the end is a reset button. The middle section, which is our RAM programming section, has our 2 read and write buttons. The bottom one is read, and the top one is write. Next to that we have our 2 read-write LEDs. Well, green is for read, and the red is for write. Our 8 data bus dip switches, and on the end is the 4 address bus dip switches. And finally on the bottom is our output port with our 8 LEDs. Let's now look at the simple program that we are going to use. The instructions that we have defined so far are load A, add A, store A, jump, and complement A. Here I have them listed with their corresponding hex values. So the program I want to write will load an initial value into the accumulator, add a literal value to it, store it on the output port, then jump to add the value again and loop indefinitely. The result should be the output port counting from 0 to 255 and repeating. To start, we'll load 0 into the accumulator using load A 0. This will load the accumulator with 0. Next, I will add 1 to the accumulator with add A 01. Then store the accumulator to address 80 using store A 80. This will set A7 on the address bus, selecting the output port. Finally, jump back to the add A instruction with jump. But it's necessary to know what address to jump to, so we need to look at the bytes as laid out in memory. Since the CPU starts running at address 0, the first instruction will be at address 00. By replacing the mnemonic with the hex value, we can see how the bytes in memory will look. In this case, load A, which has the value of 00, with the next byte having the value to be loaded by that instruction, which is also 0, 0. Following that is the instruction add A, or 0, 1, followed by 0, 1. Next is 0, 2 at address 0, 4 for store A, and 80 for the address of where to store the accumulator. Finally, the jump instruction at address 0, 6. We want this instruction to jump to the add A instruction, which from the byte list is address 0, 2. So the operator for this instruction is 0, 2. And that's the simple program, 8 bytes in length. Now let's program the Spartan, load the program in RAM, and see if it works. The board is programmed to end reset. You can see that the state count is 0, the read-write lines are high, meaning are inactive, and the address is also 0. The output port shows some value, but when first powered on, it could hold any value initially. The first 2 bytes of the program are 0, 0, so the address and data dip switches are already at 0, and I just have to press the write button. Then I'll set the address to 0, 1 and leave the data at 0 and press the write button again. Next is the address 0, 2, plus I have to set the data dip switches to 0, 1 and hit the write button. You'll notice that if I hold the button down, the values of the dip switches are shown on the LEDs, and the write LED is off, indicating that we are writing to memory. I'll continue to write the rest of the bytes. Now let's check that the program is written correctly. To do that, I'll reset the address switches to 0 and set the data dip switches all to 1s as well, just to show that they are not being used. If I hold the read button down, the address shows 0 and the data shows 0. As well, the read LED is off, indicating that we are reading data from memory. Next is address 0, 1. Pressing read shows 1 on the address bus and 0 on the data bus as expected. Going to 0, 2, data is 0, 1. Address 3 is also 0, 1. Address 4 is 0, 2. 5 is 80. 6 is 0, 3. And finally, address 7 is 0, 2. The RAM is programmed, and now we can start stepping through one clock cycle at a time and check that everything is working correctly. State 0, which is fetch 1, only transfers the program counter to the address register, so when I pulse the clock, the address bus will be 0. State 1 then loads the instruction from memory, so it sets the read line low and puts the value in memory at address 0 onto the data bus to be loaded into the instruction register. In this case, it's 0 for the load A instruction. It also increments the program counter. Now in state 2, we are in LDA 1. This loads the address register with the program counter again, which should be 1. In state 3, or LDA 2, it reads from memory at address 1, and puts the value 0 into the accumulator. And since this is the last state for this instruction, it will clear the state counter back to 0, ready for the next instruction. States 0 and 1 are the same for all instructions. The only thing that will change is the address that they use depending on where the program counter is currently at. This time, state 1 loads what's at address 2. In this case, it's 0, 1 for the instruction add A. Since state 2 has the same action for all instructions in the program, I'll cycle the clock twice from now on to get to state 3 of each instruction. Now at address 3, it will read and add the value 0, 1 to what's in the accumulator. Back to state 0 for the next instruction. Here it's reading the value at address 4, which is 0, 2 for the store A instruction. I'll cycle twice. Now it's reading the value 80 from address 5. This is the destination address of the store A instruction, so the next clock cycle will load the address register with 80, put the contents of the accumulator onto the data bus, and assert the write line. Everything looks great so far. The next cycle should now save the value 0, 1 that is showing on the data bus into the output port, since A7 is high and the write line is low. There it is, and the state count is reset to 0 for the next instruction. Now it's loading the value 3 from address 6, which is the jump instruction, and I'll cycle twice. Now we are at address 7, the last byte of the program. With the read line active, the CPU will now load the value 02 into the program counter and clear the state count as always. If I cycle one more time, the address bus should now show address 2, proving that the program has jumped back for the next iteration. There we have it. Address is 2, the read line is active, and the value on the data bus is 01, as expected from the program. Now that we know the program is working, I'll put the clock into astable mode and let it do its thing. If all is well, the output port should start counting. Off it goes. Perfect. This test setup has worked well for testing, but there is one problem. After letting the program run for a bit with the clock in astable mode, the memory becomes corrupted and no longer functions correctly like you can see here. This corruption happens quite quickly and every time it's restarted. So what's going on here? Well, after spending more time than I should have chasing this gremlin, it came down to an Electronics 101 rule. That rule being, always put bypass caps on the IC power pins. Why didn't I follow that rule in this case? To help reduce the clutter on the board. I did this because the clock runs at 100 Hz, and for this simple setup, I wrongly assumed that there was enough time for everything to stabilize before the next clock transition and noise could be ignored. If I were making a PCB for this, then I would have added the bypass caps as standard procedure as I always do. So lesson learned. Maybe it would be less sensitive if I were using TTL chips, but the CMOS ones definitely need bypass caps. After adding 0.1 microfarad caps to all the power pins, everything works as it should. Okay, it's taken a lot of steps to get here, but we now have a computer that can read, modify, and save data. There's still a lot to be desired yet, such as more instructions, more ALU functions, and more memory. But this simple CPU demonstrates all the major components needed and gives us a base to expand on. It is possible to make this more functional as is by connecting A4, A5, and A6 to give 128 bytes of usable memory. Still very small, but enough to play around with larger programs. Having to input every byte one at a time gets tedious pretty quickly, which is why the next video will do away with the manual programming and utilize an EEPROM for program storage. Additionally, since the instruction is 8 bits wide, it is possible to create up to 256 instructions, far more than likely will ever be needed. As well, the ALU can be easily expanded to 8 or 16 functions as well. I encourage you to play around with new instructions and ALU functions and see what interesting things you can come up with. Let me know in the comments what you've created. In the next video, we'll start by expanding the address bus to 16 bits and use an EEPROM from now on and do away with manual programming. I'm also excited to say that after the next couple of videos, I'll be putting together a course on this series that you will be able to get on my website. You won't want to miss that. I'll be sharing more details in future videos. So don't forget to hit the subscribe button and get notified when I upload new videos, and it really helps the channel. And if you are already a subscriber, thank you. Your support means a lot. And if you like what I do here, consider becoming a patron to help me make more great content for you to enjoy. So thanks for watching. See you next time.